Greetings and welcome to online lecture 1.3 of fluid mechanics, properties of fluid. This lecture we are going to discuss the most important properties of fluid is viscosity. The content of uh, this lecture, first of all, we'll see what is viscosity and its physical significance. Then the fundamental law associated with viscosity, that is Newton's law of viscosity, and the different types of viscosity as well. Viscosity, the term is, in brief, it is called as a resistance to flow, or to be specific, it is called as it is the property by virtue of which it offers resistance to the movement of one layer of fluid over an adjacent layer. Suppose that the fluid is flowing through a pipeline, and in this pipeline there are different layers are present. So if the fluid is moving, generally one layer offers resistance to the movement of another layer. So obviously the layer at the center offers a negligible resistance, so it moves at a faster rate, and the adjacent, so it offers resistance to the movement of adjacent layer, so its velocity reduces. So the retardation taking place. So this retardation goes on, and at the wall, that is stationary wall, the fluid particles are remain stationary. So this is what the viscosity is all about. Mainly in brief, you have to remember that it is resistance to flow, and that because of viscosity is primarily because of cohesion and the molecular momentum exchange between the fluid layers, because a thicker fluid is generally having a higher viscosity because there is more cohesion in thicker fluid, and as also some momentum exchange is there, and because of that viscosity plays. So as the temperature increases here, uh, that molecular momentum exchanges, but for liquid, I think because of this changing momentum, the viscosity decreases, or means this flowability increases. But as the flow occurs, this generally it these effects appear as a shear stresses between the moving layer that we have appeared here, we have seen here. So because of the shear stresses between the moving layers, it offers resistance as the flow occurs. But if the stationary fluid having the viscosity is because of its cohesion and its molecular momentum exchange. So suppose if we consider a stationary fluid and it's in the form of liquid, so if it's at 10 degrees Celsius, its viscosity is higher. If we go on increasing the temperature, its molecular momentum exchange increases and its flowability increases, so its viscosity decreases. So this way we can interpret this particular term viscosity. The fundamental law associated with the viscosity is Newton's law of viscosity, and in order to explain this Newton's law of viscosity, we consider two plates as shown in figure, sufficiently large, and place a small distance, a capital Y apart. The space between them is being filled with fluid whose viscosity is to be measured. So obviously, the lower plate is stationary, while the upper plate is moving with some velocity capital U under the application of force F. Uh, Corresponding to the area A, that is of the moving plate in contact with the fluid. So area A is considered as a moving plate area. And so the plate is moving with velocity U. The fluid is stationary, but the layer adheres to the moving plate. It possesses the velocity capital U, and that layer having a maximum velocity because it is adhered to the moving plate. But this layer offers resistance to the adjacent lower layer. So adjacent lower layer velocity decreases slightly, and this varies linearly here. So you can see the particles of the fluid in contact with each plate will adhere to it, and if the distance y and velocity u are not too great, the velocity u, that is a small u we can say, at a distance small y from a lower plate will vary uniformly from zero at the lower plate, which is at rest because lower plate is at rest. So the fluid adhered to the lower plate possess the lower plate velocity, possess the zero velocity, because this is a stationary fluid, and which is at rest. And this velocity increases from zero at the lower plate to the maximum u at the upper plate, upper moving plate. So this is a linear variation, but this linear variation is only valid if the distance y, and this distance y, that is the distance between two surfaces y, and the velocity are not too great. So up to that extent, this linear velocity is variation is valid. If the velocity and distance increases, so generally the variation varies with parabola or the logarithmic variation. So experiment, Newton has performed various experiment, and for different fluid variety of fluids, and for the different distances. And experiment shows that for a larger variety of fluid, the top layer always causes shear stress on an adjacent lower layer, while the lower layer causes a shear stress on adjacent top layer. So this shear stress, that is shearing action, happens because of this shear stress. And this shear stress is proportional to the rate of change of velocity with respect to y. So the shear stress is denoted by tau. So mathematically, we can have that tau, that is shear stress, is proportional to the rate of change of velocity, that is du by dy. So if we consider the proportionality constant, so this proportionality constant is mu. So tau is equal to mu into du by dy. So this equal sign is not required. The tau is proportional to du by dy. So instead of proportionality constant, we can use this constant mu, so which is also called as a proportionality constant, or a viscosity, later on it is called. So tau is equal to mu into du by dy. So this equation is called as a Newton's law of viscosity. So Newton's law of viscosity is tau is equal to mu into du by dy. So this equation is generally valid if the distance between two plates, the distance between two surfaces, not too great, and also the velocity is very low. So under these circumstances only, this equation is valid. If for larger distance and for the larger velocities, this particular equation may not give accurate values of either shear stress or the dynamic viscosity as well. So there are various forms of Newton's law of viscosity generally required for solving problems. So this is a differential. Original form is differential form, where the velocity du by dy, that velocity gradient, is given. So this equation is generally used if u is given in terms of y, small u is given in terms of y, then this equation is valid. Otherwise, the integral form equation is used if du is capital U minus 0 and dy is capital Y minus 0 in the previous diagram. So we can convert this equation, because for linear, we can take, instead of du, that is final velocity minus initial velocity. Initial velocity is 0. So instead of du, we can put a capital U. And instead of dy, we can put capital Y. So tau is equal to mu into u by y. Or tau is nothing but shear stress, which is force divided by area. So force upon area, that is equal to mu into u upon y into area. So instead of shear stress and divided by area. So this area, if we take on this side, so force is equal to mu into u by y into A. So where tau is shear stress, which is Newton per meter square. F is shear force. So if you take force on this side, actually it is misprinted. So this equation is for a shear force, F. F is equal to mu into u by y, because instead of tau, we can put F by A. And so F is equal to mu into u by y into A. So this is shear force in Newton. A is the area, very important terminology, that is A, which area is to be taken. So generally, the area, while solving problem, this confusion arises. So generally, this area is area of the moving surface, which is in contact with the fluid. So the area which is in contact with the fluid is considered, that is a moving surface. Mu is proportionality constant, which is also called as coefficient of viscosity. Later on, it is called as dynamic viscosity as well, because dynamics is all related with the forces involved. So as it is obtained from shear force, it is also called as a dynamic viscosity. It is also called as absolute viscosity as well. Its SI unit is Newton second per meter square, or Pascal second, or kg per meter second. Generally, these different forms of unit we have to memorize, because all have same, that is Newton second per meter square, Pascal second, kg per meter second, all have same unit. Its commercial unit is different, that is in Stokes, but du by dy, its velocity gradient, which is also called as rate of shear strain, or we can say the rate of deformation as well. So its unit is s raised to minus 1, second raised to minus 1. So these are the terminologies you have to memorize well, or you have to understand this terminology, because while solving the problem. So most of the cases, the Newton's law of viscosity, if it is asked in oral examination, so most of the students, that is stress upon strain, or it is shear stress is proportional to shear strain. So it is not correct definition. So generally, Newton's law of viscosity, in a statement of Newton's law of viscosity, is it is uh, shear stress is proportional to rate of shear strain, or shear stress is proportional to a rate of deformation. So it states that. So this is a statement of Newton's law of viscosity. So not shear strain, but it is rate of shear strain, because it is only strain is dimensionless, but it has a dimension, that is s raised to minus 1. That's why it is the rate quantities. Capital U is linear velocity of the moving surface, uh, which is also equal to velocity of layer adhered to the moving surface. So we can consider that moving surface area, we can velocity we can consider as capital U while solving problem. Y is the distance between stationary and moving plate or surface. So the distance between two surfaces is called as capital Y. The dynamic viscosity is one type of viscosity. So according to Newton's law of viscosity, if we see mu is equal to tau upon du by dy, and if you put the units of tau and du by dy, so it comes that is Pascal second, or Newton second per meter square, or kg per meter second. From above equation, we can construct the definition of dynamic viscosity, because it is the ratio of shear stress to the rate of shear strain. Or we can define as the shear stress required to produce unit rate of deformation, or unit rate of shear strain as well. So this is a dynamic viscosity. It is called as dynamic viscosity because it involves force, because force is generally Newton. If it's in unit, we will see this in dimension analysis, the various properties, that is properties of kinematics, properties of, or the dynamics property, why it is called as a dynamic or kinematics. So as it involves force, it is called as dynamic viscosity. The SI unit is Pascal second, uh, but its commercial unit is Poise, and the difference between 1 Newton second per meter square, that is equal to 10 Poise. So obviously SI unit is, always remember, SI units are always uh, that greater than the commercial unit. The commercial units are always smaller than the SI units. So if we have to convert uh, commercial unit to SI unit, its value decreases. So 1 poise, that is equal to 0.1 Newton second per meter square. And if we have to convert generally SI unit to commercial unit, its value increases. But obviously, while solving problem, we use SI unit. So most of the problem statement, commercial units are given. So remember, while converting this, its value decreases. That part you remember. That is very important consideration, because most of the time we confuse, either we multiply by 10 or divided by 10. This, if you remember this way, it is easier for you, because while solving problem, if it is given in commercial unit, then you can uh, divide by 10. So its value decreases. So this is about dynamic viscosity. It's already called as absolute viscosity, or it is proportionality constant term in Newton's law of viscosity. The second term generally frequently arises in the uh, problems involving viscosity, and frequently the term arises, that is the ratio of dynamic viscosity and mass density. And the ratio of dynamic viscosity to mass density is known as kinematic viscosity, and it is denoted by symbol nu, the Greek letter nu, so that if nu is equal to mu upon rho, so if we construct the unit, its unit is meter square per second. So there is no force term, no kg term involved here. That's why it is called as a kinematics, because kinematics is all about length and time, or length, time, and speed. It has nothing to do with the forces involved. So that's why this particular viscosity term is called as a kinematic viscosity. As it involves only the magnitude of length and time, it is called as kinematics. SI unit of kinematic viscosity is meters square per second, but its commercial unit is also there, that is Stokes. So 1 meter square per second, that is equal to 10 raised to 4 Stokes, or we can say this 10 raised to 4 centimeters square per second. So most of the commercial specifications, the commercial units are used, but we must know what is the relation between commercial unit and SI unit. Again, as said in earlier previous slide, that commercial units are smaller. So if it is given in commercial unit, we have to multiply by 10 raised to minus 4 to convert it into a SI unit, that is meter square per second, because we require SI unit for solving problems. So 1 meter square per second, that is equal to 10 raised to 4 Stokes. So that's it about the viscosity. So at the end of this particular topic, you should be able to define what is viscosity. More concise way it is, remember that is, it is resistance to flow. You should be able to explain Newton's law of viscosity. Generally, if the Newton's law of viscosity is asked, it is shear stress. It states that it is shear stress is proportional to the rate of shear strain or rate of deformation. Or you can say that equation, that is tau is equal to mu into du by dy. That way we can explain, but there is a limitation of Newton's law of viscosity. It is only applicable if the fluid is thick, or one thing, if the distance between the flowing surface or the distance between two mating surfaces are very less. So generally in lubrication part, the distance between two surfaces is very small. There we can apply, and the speed is low. So if the speed is large, then the distance should be very low. So either of these conditions should be satisfied. The fluid is thick, the distance between two surfaces is less, very small, and the speed is very low. Either of these three conditions must satisfy in order to apply this Newton's law of viscosity. So you should be able to apply this Newton's law of viscosity while solving problem in coming lectures. Then we have to also discuss the two types, that is, you should be able to differentiate the two types of the viscosity with their units we have to memorize, that is dynamic viscosity and kinematic viscosity. Why the dynamic viscosity is called as dynamic viscosity and kinematic viscosity is called as kinematic viscosity. Their units are important. Their SI units, their commercial units, you have to memorize as well. So this is very important topic, only dedicated to viscosity, but most of the problems are based on the viscosity. So you have to understand this particular topic thoroughly. With this, we have completed this particular topic, and thank you very much.